Hello and welcome to the Chapter 2 introduction. So, Chapter 2 is titled, or is about atoms, molecules, and ions. So, we'll discuss things like the atomic theory of matter and the discovery of atomic structure. I think this is kind of interesting. We'll get into how it is that we know that atoms are comprised of things like protons, neutrons, and electrons. Protons carrying the positive charge, protons and, neutrons residing within the nucleus of the atom, electrons orbiting the outer part of the nucleus. We'll come to some bit of an understanding of how we know about that here in this chapter. We get into that modern atomic structure, how we can count up the proton and neutron count and consider the number of electrons. Likewise, we'll get into atomic weights, figure out how much the different elements weigh on average on the periodic table. We'll then look at the periodic table, get a basic introduction into some general group trends. Not a whole lot of of these group trends. We'd spend more time on that in chapter 7 later. But then we just want to get into some basic molecules, molecular compounds in terms of formulas and naming some key compounds. Same thing with some key ions and some ionic compounds. We want to get into understanding a little bit of the nature of what we tend to find in terms of common ionic compounds, get a sense of what these formulas look like, and then get a sense finally of naming some inorganic compounds like salts and acids, binary compounds, and we'll go through and describe what these are as we get into the notes, and then also some simple organic compounds like hydrocarbons and alcohols. So as we look through our learning objectives in this chapter, we're going to want to look at what this Dalton's atomic theory is and understand that. Look at the key experiments that led to the discovery of the electron and the nuclear model of the atom. So these will be things like the cathode ray tube experiment finally came to me. And the cathode ray tube experiment is going to be the key one that helped us discover the subatomic particle that we call the electron. We will then talk about the Millikan oil drop experiment that helped us determine the charge on one electron and also the mass of an electron. Then we will get into things like the nuclear model coming from Rutherford's gold foil experiment, how we can shoot a beam of particles at gold foil and see if those particles are deflected or if they go straight through. This helped develop the idea of the nucleus of the atom. Also, we'll talk about Marie Curie's experiments on radioactivity and some of those basic experiments. This will help us get into the structure of the atom in terms of protons, neutrons, electrons. We'll get into electrical charge, masses of the subatomic particles. We'll see that the electron's very light, the proton's much more massive, but their charges are actually opposite of each other. So our electron charge and our proton charge are equal in magnitude but opposite in sign. We'll use chemical symbols in the atomic number to help us get a sense of the different elements on the periodic table. We will then try to come up with the atomic weights of the elements as the masses of the individual atoms, looking at their atomic abundances, or their natural abundances. So, for example, carbon-12 is about 99%, maybe 98%, somewhere in there, percent of carbon is carbon-12. About 1% is carbon-13. This is roughly, so it's like 98.8 or 9% is carbon-12. The most is carbon, or the next most abundant isotope of carbon is carbon-13. So isotopes are different by their neutron count, the neutral particle. So if we add an extra neutron to the nucleus of carbon, that becomes carbon-13, and then its abundance, it's much less abundant in a natural sample, say on the surface of Earth. Carbon-14 is present to a very, very small percentage. I think it's less than 10 to the 10%. So carbon-14 with one more neutron, this abundance is less than 10 to the minus 10%. So that's really low in abundance for that particular isotope. But we'll get a sense of how the specific abundances of the isotopes of a given element and what their masses are contribute to the average atomic weight that we list for a particular element. Where this comes into play, if you look at a periodic table, you'll see, most of the elements have their noted mass underneath the elemental symbol. that mass is referring to the average atomic weight of all of the naturally occurring isotopes for that particular element. So getting on and looking at some of these other objectives, and one of the keys is that, at this moment, not every one of these objectives will make sense, but keep these objectives in mind. This is kind of what we think of when we write our test, that we're just going through the different sections of the book and trying to come up with what the main ideas were within those sections. Like, we want to describe how the elements are organized in the periodic table by atomic number and then by similar chemical behavior. So the sort of columns in the periodic table tend to have similar properties, but then the rows, as we go from left to right across the periodic table, not as similar properties from left to right. We actually have more metallic elements on the right side, more non-metals on the more metallic elements on the left side, more non-metallic elements on the right side. So we get a pretty big difference in the element trends from left to right across the periodic table. We can get a basic sense of what some of these different trends are here in Chapter 2. We'll spend more time on that when we get to Chapter 7. We want to identify the locations of the metal and non-metal elements in the periodic table. Again, we were just talking about this, metals on the left side, non-metals on the right side. We want to distinguish between molecular and ionic substances. We talked a little bit about this in lecture during our second lecture, where we were talking about the difference between like water being a molecular compound and NaCl being an ionic compound. We'll take a look at that in more detail here in Chapter 2. We want to distinguish between empirical and molecular formulas. Now, an empirical formula versus a molecular formula, if we think of like hydrogen peroxide, H2O2 is the formula for hydrogen peroxide because a molecule of hydrogen peroxide contains one H, an O, and another H. So it contains specifically 2 hydrogens and 2 oxygens. So this is really what's important for hydrogen peroxide. For most molecular compounds, their molecular formula is the most important information we would want to have. But then we could say, well, the empirical formula for something like hydrogen peroxide would be HO, 1H to 1O. So this would be the empirical formula. The simplest whole number ratio of H and O is 1 to 1. Now, this doesn't really tell us anything, or it's really not that useful to know that that is the empirical formula for something like hydrogen peroxide. But what we're going to see, or that we can maybe appreciate, is that for ionic compounds, all we ever really know is their empirical formula. Like we were talking in class, like something like NaCl, we don't ever really encounter in nature 1 sodium and 1 chloride bonded together for one specific group. We really see a tremendous number of repeating plus and minus cations in nature, so that when you encounter a salt crystal, you're probably not going to call it, something like Na, 700 Cl 700, where you have 700 each of your plus and minus cations. You're probably just going to say, well, why don't we just agree that for ionic compounds, we'll just simplify and give their empirical formula as what we consider to be their most useful representation. We'll also see how you can experimentally find empirical formula from experimental data when we get into Chapter 3. So we might find later that we can find an empirical formula, whether it's a molecular and ionic compound, from some experimental data, and then maybe from some additional experimental data, if it's a molecular compound, we can figure out that substance's molecular formula. So that's a topic we'll get into. Maybe you could recall that type of example from your high school chemistry, but we'll get into that in Chapter 3. So then, so where are we here? So distinguishing between empirical and molecular formulas is pretty easy here in Chapter 2. So molecular formula here for like H2O2, its empirical formula would be HO, and we're just kind of knowing that we're learning that difference just so that we can see the next topic, the next chapter, where we find the one formula experimentally and then the other one with some additional experimental information. We want to determine how molecular formula and structural formulas are used to represent the composition of molecules. So kind of just like we're talking about with H2O2, that for the molecule, that there is some connection of 2 hydrogens and 2 oxygens together somehow within that molecule. In terms of like a Lewis structure, we won't get into a formal discussion of those until we get to Chapter 8. We might sketch a couple here in Chapter 2 to give you a sense of what these compounds kind of look like in terms of their molecular connections, their covalent bonds, but you're not going to be responsible for predicting those types of structures until we get into Chapter 8. So we want to explain how ions are formed by the gain or loss of electrons. So sodium on the periodic table would contain 11 electrons. If we go to sodium plus, it would have lost an electron. Perhaps it was picked up by chlorine, which normally has 17 electrons. which then picks up that extra electron to go to 18 electrons. So the chloride ion, 18 electrons, sodium ion, 10 electrons. We'll try to see why those are relevant. If you're looking at a periodic table, sodium just loses 1 electron, comes up with that noble gas count, that special count of electrons that's especially stable. Chloride gains an electron. So it's really easy for the elements on the far right side or the far left side to gain electrons on the far right side, like the halogens, and then lose an electron if you're like in the alkali group with sodium, potassium, rubidium, things like lithium. That's relatively easy for those elements to lose an electron, and then they exchange, pair up, and then they end up forming these electrostatic linked ionic compounds. So then we can write empirical formula for ionic compounds. That's their most important formula to understand, is their empirical relationship between the ions and those compounds. We want to give the charges of the component ions. Like if we're looking at something like calcium chloride, we want to be able to look at calcium, it's in the alkaline group, that it's a 2+, and chloride's a minus. There's 2 of them for a -2 overall, balancing out the charge. May not be able to do that just now, but that's what we're kind of talking about, getting into classifying charges and giving those for the different ions within compounds. We want to be able to write names for ionic compounds if we give a formula, or write a chemical formula given its name. So we often will say name to formula or formula to name. We will give you I'll give you a list of the things I think you need to know how to name for the class a little bit later within the notes. But we'll have hopefully a pretty definitive set of things that we need to memorize or just understand with a nomenclature system for how we're naming these types of ions. There is a system, so you shouldn't feel like you have to memorize a whole lot here, but there'll be some rules that we're learning, and then we're applying it to some different types of ions. And then we want to name and write formulas for things we'll call binary, inorganic compounds, and for acids. We'll describe what those are later. And then identify organic compounds like simple alkanes, those are hydrocarbons, and alcohols, and be able to name those. So things like methane, CH4, methanol, CH3OH. So right now you can already get a sense that, well, if this is methane and this is methanol, that seems pretty systematic. And it holds true that if you know C2H6 is ethane, and then you replace one of the H's with an OH group, just like we did on methanol, if you go to C2H5OH, that's just ethanol. So it becomes very systematic on how we're naming compounds. Okay, so let's actually get close to wrapping up here by actually going through and naming a few things that you may already know how to name. I think there was a similar type question on one of the intro or on the first recitation activity, because a lot of these things you may already know how to name or can probably envision the name. So Na, of course, is sodium. So that's the ion name. So that's sodium nitrate for the first one. So the second one, that's a different compound. So we can't call this sodium nitrate as well. I think we can agree that if you have NaNO2, which have a different name than NaNO3. So if NaNO3 is nitrate, we lose an oxygen. The systematic name here ends up being sodium nitrite. So that if you ever know an ATE ending ion that's lost an O off the formula, then that just takes the ITE ending. So nitrate is NO3 minus, nitrite is NO2 minus. So we just lost an O atom. The charges remain the same. We got sodium plus and sodium plus in each case. So sodium nitrite. Now HNO3 ends up taking the systematic name of nitric acid. I'm sure you've seen that name before. And then HNO2 should also have a different name. The ite acids end up becoming us. So this ends up going and being named nitrous acid. We have HNO2, nitrous acid, HNO3, nitric acid. So any anion that has an ATE suffix, it just goes to ic acid when we are naming the acid form of that particular anion. So the names of the acids kind of go with the anions. The anion names are linked together with the ates and the ites. We'll even learn that a per-ate has an extra O, and then a hypoite has one fewer O. Not all of our ions actually do that sort of process. So we'll learn how to name things like ClO3 as chlorate. If you add an O and go to ClO4 minus, that's the per out in front. So that's perchlorate. And then if you lose the O, like we said before with nitrate, we should know that that's chlorate. ITE for chlorite. If you lose another O, go to ClO minus, and that's hypo. And that's chlorite. So we got two ites, two eights, a per and a regular, and a hypo and a regular. And then you can imagine the same thing happens if we have bromine or iodine for the other halogens. Fluorine doesn't form these types of oxy anions in this kind of case, like chlorine, bromine, and iodine do. But if you replace the chlorine with a bromine, guess what? It just becomes bromate, bromite, hypobromite, perbromate. And the same thing with the iodine atom. It just becomes like periodate, iodate, iodite, and hypoiodite. So names become very systematic. That's what I'm trying to show you with this kind of introduction here, giving you a quick sense of that as we get started on this chapter. There's methane and methanol. I won't write them out, but that's how we would name CH4 and CH3OH. So finally, let's wrap up with the problem here about carbon. We mentioned earlier it's about 99% carbon-12, more specifically 98.93. Maybe we could talk later about why carbon is 12 AMU exactly, and it's actually a little bit jumbled now because the International Union of Pure and Applied Chemists have actually changed the way some different fundamental units are actually defined. It used to be that carbon-12 was defined exactly as 12 AMU, and that is kind of still a good way to look at it, that the carbon nucleus kind of sets this AMU scale. There's a good reason why we picked 12 AMU. We'll maybe see this work out a little bit later when we get into chapter 3, but for now it doesn't really matter. We're picturing one single carbon atom has a mass of 12, and the unit here is atomic mass units, and then it's exact. So we're imagining that this is some definition of a mass scale that's defining the carbon nucleus is exactly 12 AMUs. But then the carbon-13 nucleus, which has an abundance of 1.07%, so just about all the remaining carbon, or all the remaining carbon is carbon-13. A very tiny trace is carbon-14, so almost none of the carbon in a natural sample is carbon-14. Interestingly, there's enough that you can date samples that are pretty old by their carbon-14 that they still have left in them. That's a topic for chapter 21 later. It doesn't have much to do here, but in case you're wondering, you've heard about carbon dating, you can actually date a sample by how much carbon-14 it still has within it. It's an interesting topic, doesn't really have much to do with what we're talking about here, but the key is that the carbon-14 trace is 10 to the minus 10% or even lower if you have like a sample that's no longer natural. If it's like a dead or decaying sample, it'll have even less of a percentage of carbon-14 than this. And that is almost, doesn't even hit on the 1.07, so, it's just such a tiny trace as carbon-14. So what we want to do is calculate the average atomic weight of carbon. Okay, so the average atomic weight of carbon, if we think about it, it should just be, the percentage of carbon or even the fraction of carbon that is carbon-12 times the mass of carbon-12, and then plus the fraction that is carbon-13 times the mass of carbon-13. Now the mass of carbon-13 isn't like 12, it's not exact, so this is an experimental value with only 6 digits given, or 6 digits that are known. And I transcribed one of the numbers down wrong, let me clean this up. So this would be 1.07%, or expressed as a fraction. 0.0107 of a fraction is carbon-13. And if we add these up, let's actually do the adding up over here. So I can do the 0.9893 times 12. Now the reason why I was highlighting and really focusing on the 12 exact here is that when I get 12.87 here AMU, when I factor carbon in, transcribing that wrong too, it's 11.87, not 12.87. So it's 11.87 when I do this arithmetic here, and then I'm going to add to that the 0.0107 times 13.0034, that works out to be 0.139. Now if I'm keeping track of my sig figs, I keep like all 4 sig figs here because this 12 AMU is an exact number, so it's not an inexact quantity, so I don't round the 11.87 to 2 significant figures. I keep all 4 from the fraction, from that percentage that I'm using. And the same thing, I'm going to keep 3 sig figs times 6, so I keep 3 on the final result here. I add this up to 11.87 AMU, and I get 12.01. So the average atomic weight of carbon is a little bit more than 12. It would be exactly 12 if carbon was 100% carbon-12. And we see that since carbon's about 1% carbon-13, that the average atomic weight of carbon is a little bit higher than carbon-12. So if you're picturing the mass is somewhere between 12 and 13, it's much closer towards carbon-12 because that's where the abundance is. Most of the abundance of carbon is that carbon-12. So now where this becomes useful, and it's kind of interesting that we don't quite use the atomic weights in this chapter yet, where this mass is going to be useful is when we start picturing having a large collection of atoms. If you have, say 100 carbon atoms, roughly 99 should be carbon-12, the other one should be carbon-13. So the mass of that sample should end up being reflective of that ratio. So when we start working with like the mole units or having like a lot of grams of carbon, it's going to be really useful for us to use the sort of average weight that carbon is, not the very specific weight that one of the atoms of carbon happens to be. So if you have an atom of carbon, its mass should either be 12 AMUs or 13.0034, never really 12.01 AMU, but if you have a collection of carbon atoms, that average weight is going to be what's really useful for doing problems where maybe you need to convert to moles. And then the only thing to know at this point is we won't really get into those calculations until we get into chapter 3. So we're kind of learning about the average atomic weight so we can use it in the next chapter. And so maybe at this point, or as we do this problem in this chapter, I think it sometimes is confusing of why we're learning about average atomic weights, but it's a really important number to understand because all we need to do is take the abundance of a particular element times its mass, add those all up for all the natural occurring isotopes for a given element, and then that helps us get the average atomic weight for that particular element. So this is just one of the key problems from chapter 2. So hopefully this video here gives you a little bit of a better sense of what's to come in chapter 2, of what to start paying attention to as you come to class, do your readings, or maybe watch the chapter 2 summary video. So thank you for the attention.